Okay, for what we're going to be looking into is going to be zeros of polynomials. And now we've been looking at polynomial functions all along, especially in the case of working with equations. And now for what we have regarding zeros of polynomials, we've looked at factoring expressions and working with quadratic equations and equations of various types, as well as different degrees. Now, if you notice at the top of the screen, okay, we have underneath the title, zeros of polynomials, okay, we have what is referred to as the multiplicity of a zero. And by definition, the multiplicity of a zero is the degree to which the factor corresponding to that zero is going to be raised. Okay. And now, for what we have in terms of graphing, okay, we're going to have some odd-powered as well as even-powered functions, and pertaining to what we have in the zeros. Okay, now in graphing, the graph of the function f of x, but it could be g of x, h of x, and whatever the function expression is, that's just going to be what we otherwise say is going to be what we have for y. Okay, so we have in graphing, f of x is going to cross the x-axis at zeros of odd multiplicity. Okay, but now for even-powered expressions, we have for those zeros are going to have what will be regarded as even multiplicity, and we're going to have the f of x touches but does not cross the x-axis at zeros of even multiplicity. Now, as an example of a function, and we will have this on display in factored form, and it says here to determine the zeros and multiplicities of f of x is equal to the cube of the quantity of x plus 2 times the square of x, and we have times the quantity of x minus 2. And I'm including the 1, okay, since we have implicitly that the degree of the expression, or at least for that factor, is only going to be at 1. Now for the zeros of f of x, okay, we have from x plus 2, if you set x plus 2 equal to 0, x is equal to negative 2. Next factor in x, okay, we have just x, and if I just set to 0, this comes out automatically to 0. And as for x minus 2 equal to 0, we have that x is equal to 2. Now for the multiplicities of what we have for the zeros, okay, we have for x is equal to negative 2, this stems from x plus 2, which is raised to the third. Thus, the multiplicity of x equals negative 2 is going to end up at 3. And for x is equal to 0, this stems from x, which was raised to the second power. So 0 has a multiplicity of 2. And again, x equals 2 originates from x minus 2. Okay, and that was the first order. So 2 is a multiplicity 1. And again, considering that for the zeros that have odd multiplicity, in other words, the zeros that originate from factors that are raised to odd number powers, it will be at those zeros that the graph is going to cross. Okay, so we have with negative 2 and positive 2. Okay, those zeros have odd multiplicity. So we're going to have to cross at x equals negative 2, and also at x is equal to positive 2. And since 0 has an even valued multiplicity, okay, it is at x is equal to 0 that the graph is going to touch. And in looking at what we have for the graph of this particular function, okay, and if you notice, okay, we have our three zeros. So you have negative 2, x equals 0, and x is equal to 2. And if you notice, okay, we have x equals negative 2, you have to cross the x-axis. And once we get to 0, 0, okay, we have at x is equal to 0, the graph touches but does not cross the x-axis. And then we have with x is equal to 2, the graph is going to cross. And again, just a little re-examining. If you're looking at attaining the zeros, the multiplicities that correspond, as well as whether the graph is going to cross or touch the x-axis. Now we have with number 2, for this function that is given in factored form, notice we have a leading coefficient, 5, and this is just a constant. So this does not do anything for us in terms of attaining the zeros. It's just a constant. It is not interacting with x in terms of addition, subtraction, multiplication, or division. But for the x factors, we have x minus 11, which is to the first, and x minus 12 is to the first, and those zeros we have respectively at 11 and 12. And again, those zeros each will have a multiplicity of 1. Now for x plus 3, that factor, the corresponding zero, we have at x is equal to negative 3, and we have raised to the second, so we have a multiplicity of 2. And for x plus 11, we have x is equal to negative 11, and that multiplicity we have to be at 1. So again, for the zeros of odd-numbered multiplicity, we have the graph to cross the x-axis. So we have crossing at 11, x is equal to 12, and x is equal to negative 11. And since x equals negative 3 has an even-valued multiplicity, it is at x is equal to negative 3 that the graph is going to touch the x-axis. Now, in terms of just some of the dynamics that play out, and we have with, say, just going back to intercepts, and we have for this particular polynomial function, and this is one that can be factored by grouping, and for the determination of the intercepts, again, for the x-intercepts, you're looking at solving for x as you set that which represents y equal to 0. So we have for this particular polynomial function, okay, now we had the proportion of the coefficients and the degrees to be such that I can factor by grouping. So if I take the first two terms, so I have the quantity of 2x cubed plus 6x squared, and again, the middle operation is going to be subtraction and quantifying the representation of negative 2x minus 6. So I have factoring out a negative sign. So I have the negative of the quantity of 2x plus 6, and just taking what we have here and just illustrating. Okay, so the greatest common factor, again, of 2x cubed plus 6x squared, that's going to be 2x squared. And for that of 2x plus 6, okay, we have 2. And again, I already have brought down the subtraction. And if you notice, upon factoring out 2x squared into 2x cubed plus 6x squared, that's going to be x plus 3. And for 2 into 2x plus 6, you have also at x plus 3. And so we have the common binomial factor. We're going to have at 2x plus 3. And combining, once again, the outside terms and operation, we have 2x squared minus 2. And here we have a multiple of the difference of squares. Okay, so you have x plus 3 already factored out. And 2x squared minus 2 I can factor out further. So I can draw out the coefficient 2 into 2x squared minus 2, I have the quantity of x squared minus 1. And then for the complete factorization, okay, so in shifting the coefficient 2 out the front, okay, we have x plus 3. And from x squared minus 1, I have the quantity of x plus 1 times that of x minus 1. And the zeros that we have with the x-intercepts, so we have x equals negative 3, another x-intercept at x equals negative 1, and one more that we have at x is equal to 1. And if I display in coordinate fashion, we have for the x-intercepts, I have negative 3, 0, negative 1, 0, and also positive 1, 0. As for the y-intercept, okay, again, we're looking at solving for y as x is set to 0. And if you notice in the polynomial, okay, the first three expressions are going to become negligible since we're setting x to 0. And then we have, at the end, we had the constant negative 6, which is going to remain. And so we had the y-intercept at y equals negative 6, and thus our y-intercept we have at 0, negative 6. And we have on display the graph itself, so we have with the x-intercepts, so we have negative 3, 0, negative 1, 0, and 1, 0. And again, the y-intercept we have at 0, negative 6. Now, and we're going to soon be looking into the end behavior of the graph of a function.